Hello everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying functions lecture 1. Now functions is also going to be another lengthy lecture series just like trigonometry because there are too many basic concepts that are involved and these are the basic building blocks of your entire calculus. So just pay attention to all the basic concepts and practice a lot. So let's get started with the discussion. So this is question 10 of QOD series. Just take a screenshot for that. Now, before starting this basic definition, I'll go with the other definitions because I'll come to this slide after discussion of domain and range and codomain. So let's look at the mathematical definition of functions first. Mathematical definition says function is nothing but any relation in which every element of A is mapped and has only one single image, exactly one image. So basically in relations, what used to happen is, let's say there was an element D over here, and if this was the marking, if this was the mapping, sorry, then it would have been possible that D might be left out. But in case of functions, it won't be the case. They won't be left out. So every single element of set A is going to be mapped, sorry. So this is set A, this is set B, and we have this given function over here. So let's define one function, f equals to a comma 1, b comma 1, c comma 2. So a is being mapped to 1, b is also mapped to 1, and c is mapped to 2. Now interesting point is, in case of set B, there can be elements which are left out. Like in over here, 3 is left out. It's not being mapped. But in case of A, every element should be mapped and has only one image. It cannot have two images. It cannot have like this. This is not possible. If this is the case, then this it's not a function. It's simply a relation. All right. So these all elements are being mapped. Now let's take one more example. Let's say we have this as given the relation. Is this relation a function or not? And this is not, because A has two images. A has one over here and two over here. A has two images. In case of B, it's three images. Also, C is not being mapped. If this is happening and if this is also happening, it's not a function. If this alone is happening, then also it's not a function. Let's say if this is also mapped, then also it's not a function because it has two images. And let's say if this is happening, A just has one image, B has one image, but C doesn't have any image. In that case also, it's not a function. All right. So this is the basic definition of functions, mathematical definition of functions. We'll talk about the criteria on how to decide if this element is going to be mapped or not. Now let's talk about domain, range, and codomain. Now remember the discussion in relations. We got to know that every element which is being mapped from set A is the domain. Same is the definition over here, but over here, now in this case, we cannot leave any element over here. Like for example, D is over here. You cannot leave D. In case of relations, we could have left, right? But in case of functions, we cannot leave it. So in case of functions, domain is nothing but set A comma B comma C. D is not there. Now talking about codomain is same as set B, that is 1 comma 2 comma 3. Now talking about range, in that case, let's define one function. A is being mapped to 1, B is being mapped to 2, and C is also being mapped to 2. In this case, these are the elements, these are the images. So the images are the range, nothing but the collection of all these images, all these elements is the range, 1 comma 2. So that is same as a relation. So 3 is not the part of range. 3 is the part of the codomain, but 3 is not the part of range. Now coming back to again this first slide. Now how do we decide that this particular arrow diagram from A, B, C, and so let's have a practical or analytical view over it. Make sure that you have a practical or analytical view over it. Mixer or juicer. So let's say this is our juicer. We cannot give stones or wood or anything else over here. And only if we give input as fruits, then only we'll get some decent output. desired output, right? Otherwise this function won't work, this juicer won't work, right? So that is how we decide if A is going to be mapped or not, B is going to be mapped or not, C is going to be mapped or not. So basically we have a function over here, fx. Now if this A, B, C is a relevant input or not over here, that only will decide that A, B, C is going to be mapped or not. Got the point? So that is why I took this slide afterwards. Now we all know about inequalities and intervals, but I'll just give a refresher so that everyone get in touch with it again. So let's talk about number line first. Number line and its notations. So this is point 0. So let's say we want to define a range. So these are two common symbols which we use in number line. What does these mean? Let's say if I want to include all the elements from let's say -3 to 2. We'll talk about the brackets later. So what we'll do over here, at -3 I'll use this open circle, and at 2 I'll use this closed circle. So basically this means at open circle 3 is not being included, but at closed circle 2 is being included. So this is how I define a range. This range means all the elements between -3 to 2 where 2 is being included but -3 is not included. Now if I want to represent this in the bracket form, then what I'll do, I'll use the curved bracket or the parenthesis, or I'll and over here I'll use the square bracket. So what does this mean? This means this curved bracket means that open circle, and square bracket means closed circles. Basically 2 is included and -3 is not included, right? If I write it like this, -3 comma 2, in that case -3 is included but 2 is not included in the range -3 to 2, all the elements except 2, right? So this is basic refresher about the intervals. Now let's talk about inequalities. Let's say if I write x minus 2 greater than 0, that means x greater than 2, right? This is very common, we have used it many times. And this is greater than sign. So basically if I want to write this inequality in terms of bracket form, what I'll do, I'll write 2 to infinity. So 2 is being open, 2 is written with open bracket. And if I want to plot it in number line, I'll do like this. This is 2 open circle over here because 2 is not included, and till infinity, right? Now if I mark less greater than equals to over here, in that case I'll do close circle over here because 2 is included, and in terms of bracket I'll write close to infinity, right? So this is the basic refresher about inequalities and intervals. Now let's discuss about wavy curve method. And before starting with the rules of wavy curve method, I'll try to build the intuition. How did we derive the basic rules and formulas? So let's take one basic example first. Let's take x plus 3, x plus 1, x minus 1 greater than 0. So if I want to find the solution of this inequality, I want to find all the ranges of this inequality, what I'll do, I'll mark simply a number line. Then I'll mark the critical points. What are the critical points? Critical points are those points at which this particular element or this particular bracket zone becomes 0. So x plus 3 becomes 0 at -3, x plus 1 becomes 0 at -1, and x minus 1 becomes 0 at 1. Now one can clearly understand or say that this region, this entire region, greater than 1 region, is always positive. Why? Because x, this term will be positive, this term will be positive, and this term will also be positive. So everything beyond 1 will always be positive, right? So I'll mark it as plus zone. From here I'll mark it as plus zone. Now talking about this zone, -1 to 1, in that case this will be negative, right? But this will be positive and this will be positive. So overall product will be negative. So I'll mark it as negative zone. Now let's talk about -3 to -1. In that case, this will be negative, this will be negative, but this will be positive. But we have two negatives over here. Again, that will be positive. Now, if we go beyond -3 in the left side, then everything will be negative, right? In that case, this will be minus, because we have three products. Three elements over here, 1, 2, 3, and all three are negatives. That's why this is negative. Now I can see one pattern over here, that is plus minus plus minus, but it's too early to say that this is going to be case for every situation. So let's take few more examples. Let's write x plus 3. Maybe we can write x plus 5 over here, and we can write x plus 1 and x minus 1 greater than 0. Now what I'll mark the critical points. This is minus 5, minus 3, minus 1 and 1. So I can clearly see that if x is beyond 1, x is greater than 1, in that case all these multiplications will be 1. This will be positive, this will be positive, this will be positive, and this will be positive. So everything will be greater than 0, right? So I can mark it as positive zone. Now over here again, I can write it as negative zone because only this one will be negative, rest will be positive, right? This one will be positive, this one will be positive, this one will be also positive, but this one will be negative. So I can write it as negative zone. Now over here, if we talk about this zone, I can write it as positive because in this case, both this and these two elements will be negative and these two will be positive. So again, we can write positive. Similarly, I can write negative over here. I can write positive over here. Now I can see that we can see similar kind of pattern over here, plus minus over here. Okay. So this is we can see that even if we increase the number of elements over here in the inequality, we can see similar kind of pattern going on here. Now let's check it out further. Now let's say we have x plus 5 and 3 minus x and x minus 1. Now let's try to plot the diagram. The critical points are minus 5, 1 and 3, right? Now let's take this point, this region beyond 3. If I go beyond 3, this is positive, this becomes negative, and this is also positive. So overall becomes negative. So now a major difference comes in. Initially everything was positive over here, but here it is negative over here. So that is one change. Now let's look at this zone 1, 2, 3. In this case, this will be positive, this will be positive, and this also will be positive. So it becomes positive. Now again, I see the alternative pattern. We'll get minus over here, we'll get plus over here. So what change happened? Just because we changed one sign over here, we replaced x minus 3 with 3 minus x. In that case, we got minus sign over here. So that is not building into something, right? Because if you want to build into something, build the intuition, then we should have a one standard formula and not multiple formulas. So what I'll do, I'll try to change this entire setup. What I'll do, I'll write x plus 5, x minus 3, x minus 1 less than 0, because I multiplied minus 1 both sides. What happened? We changed the inequality, but we got the standard format. Now if I plot it, then I'll get minus 5, 1, 3. Then I'll get plus over here, minus over here, plus over here, and minus over here. You can check it. So now we get to know that everything should be written in this format. Then only we'll get plus minus over here. Otherwise, we might get minus plus over here, right? Now coming to the next point, let's say we take the same example, x plus 3, x plus 1 whole square, and x minus 1. Now if we try to plot it, these are the critical points. Now if we see beyond 1, then this is positive, right? Now if we go in this region minus 1 to 1, this is negative, this is positive, so this becomes negative. But now if we take this region, in this case this still stays positive, this is negative, and this is positive. So it overall becomes negative. Now again we have a change in pattern. Now let's look at this one. Over here, this is negative, and this is positive. So it becomes positive. Now we are not getting plus minus over here. We got plus minus plus. So what actually changed? Because we got one power over here. Now let's make it 3 over here. Or maybe I'll draw another one. Let's say this is x plus 1 cube, x minus 1 greater than 0. This is minus 3, this is minus 1, this is 1. Now this is positive. Now if we take this zone minus 1 to 1, this is negative, this is positive, this is positive. So this becomes negative. Now if we take -3 to -1, in that case this is negative. Now this is also negative because we have odd power. So this becomes positive because this is positive, this is negative, this is negative. So overall it becomes positive and this becomes negative. Now again we got the standard format plus minus plus minus. Now what we can say that whenever a critical point is being passed which has even power, in that case we won't change the sign. So we will make the first modification over here. So the rule is whenever we are crossing a critical point which has even power, in that case we won't change the sign. But in case it's having an odd power, we can change the sign. We can make it alternate, plus minus, right? So this is the one modification to the rule. Now let's look at the last example. Let's say we have x plus 3, x plus 1, x minus 1 divided by, let's say we have x plus 4. Now we got one denominator. Now this cannot be 0. So we'll always have to exclude x cannot be 4. X cannot be, sorry, minus 4. We'll always have to exclude minus 4 from any kind of equation we got, any kind of result we get. We'll have to exclude x equals to minus 4. Now let's plot the critical points. Now before plotting the number line, one more thing is, if this is in denominator or in numerator, it's not going to make any changes in the formulas or the rules, because if it's negative, then it's going to impact the entire inequality. If it's positive, then also it's going to be impact the entire inequality, regardless if it's present in numerator or denominator, right? So let's plot the critical points. This is -4, this is -3, this is -1, and this is 1. Now let's talk about this zone greater than 0, greater than 1, then we'll get positive. So we'll get the alternate signs over here. But the interesting point is we have to make an open circle over here, empty circle over here, so that we get to understand that this point has not to be included in our inequality solution. Now how to derive, let's go back to the first one, right? Now how to derive the result from it. We got to understand that how to plot the entire number line. But how do we find the solutions from here? Now we have to find the zones where this inequality is greater than 0. So we have to just find out the positive zones, right? Because we marked these zones positive because these were positive for all values of x. So if x is greater than 1, then this entire zone is positive. If x is between -3 to -1, then this entire zone is positive, right? Now since we are using inequality of this type, like it's not greater than equals to 0, it's just greater than 0. So there is no equality over here. So we'll always have the open circles over here. We'll not include these points, because at these points this entire inequality will become 0, but we don't have equality sign over here. So that's why we'll always use open circles over here. Now based on this, what I'll get -3 to -1 union 1 to infinity. So these are the positive zones only. This one is negative, this one is positive, that is -3 to -1, open brackets, because we cannot include the values. Similarly from here, 1 to infinity, open circle, open bracket, right? Now let's go back to this one. Now again, if you want to find out the final range or final solution for this one, in that case what we'll get is, we have to check for the positive zones, because this is inequality greater than inequality over here. It's not having equality sign, so we'll always use open circles. First point. So this is -infinity to -4, open bracket. Then this zone union -3 to -1, open brackets, union 1 to infinity, right? And this is also been excluded. Let's say if we had greater than equals to 0 over here, then these would have closed circles with the basic rules. But since x plus 4 is in denominator, we cannot have -4 as the answer, as the final solution. So we'll always have open circle over here in case of -4, right? Oh, I forgot to add one more point over here. So let's remove this first. Let's say we have x times x minus 5 greater than 6. Now we don't have 0 over here. We can mark the positive or negative zones only if we are comparing the inequality with respect to 0, right? So what we'll do over here, we'll, sorry, we'll take this 6 over here and write it like this. So what will happen is that will become x square minus 5x minus 6 greater than 0. And we'll try to factorize it. Let's make it minus 6 over here. So that will become plus 6. So this becomes x minus 3 and x minus 2. Now this becomes the standard format. Now let's discuss the final rules. The first one is standard formatting. What does this mean? We'll have to write equations in the format like this. Let's say this is power d, this is power e, this is power f, greater than or less than 0 over here. So we should have 0 over here. We should write our entire equations like this only. We cannot write a minus x something power like that. We cannot write like that. If it is there, we have to convert it in this format, and we have to have 0 over here because we have to mark positive and negative zones. So this is the standard format. We have to convert if it's not there. Now let's discuss the second major rule, crossing the critical point. Now, this rule says whenever we are crossing a critical point having an even power. So let's say if this is the equation x minus a x minus b raised to power 2n x minus c dot dot dot. Then in that case, whenever we are crossing this even power, in that case we won't be changing the sign. So what we used to do plus minus. But whenever we are crossing this one, we won't be changing the sign. So let's say if this one is over here, then we'll not change sign over here. And after that, we'll continue with the alterations, right? So this is the second rule. Now, similarly, for whenever we are crossing an even odd power, in that case, it keeps on happening the way it was happening earlier in a simple format. Now, third point is whenever we are having an inequality in which there is certain elements in the denominator as well. So whenever we are having an inequality in this format, x minus c, x minus d, x minus e, greater than equals to 0, then regardless of whatever the sign is over here, if it's greater than 0, less than 0, less than equals to 0, greater than equals to 0, we'll always keep open circle at d and e critical points. So whenever we are marking the zones, whenever we are marking the number line, in that case we'll always keep the open circle at d and e in case of inequality of this format, basically the denominator format. So these are the three major rules of wavy curve method. And I think, I hope you got the point how to build that intuition for it. Now let's discuss types of functions, one functions and many one functions. So as the name suggests, one function means, so let's say this is set A, this is set B, this is set A, this is set B. One function means every element of A is being mapped with just one element of B, right? It cannot be like that. C is mapped with two also. C is mapped with two, and B is also mapped with two also. It's not like that because that will be many one functions. We'll talk about it later, but let's focus on one first. One says every single element of set A is being mapped with only one element of set B, right? So this is our one function. Now talking about many one functions, then as the name suggests, mapping will be done by every element, but it can be like this, like this. So A and B are both being mapped to 1. C is being mapped to 3, right? Let's take first example. And then after we'll talk about on to into functions. So let's consider function mod x. So we all know that mod x graph looks like this roughly. We'll not go into complications, technicalities, but just to get an idea, what are one functions and what are many one functions. Now I can see that, let's say this is point x1 and this is point x2. So for x1, we have this value of y. For x1, we have this value of y corresponding to modulus function. And similarly for x2 we have again same value, right? So for two inputs, for two elements of set A, we are getting same value of set B. We are getting just one element, right? So that is why it's a many one function. Suppose there was a case, let's say it's just y equals to x. We are plotting a simple y equals to x linear line, linear equation. So in that case, for every element x1, x2, x3 over here, we get just one point, right? We get just 1 point over here. So this is a 1 1 function. For every element of A, we get just one in output in B, one element of B. Now let us talk about onto and into functions. So this is our set A, this is set B. Now let's take one example first. A is being mapped to 1, B is also being mapped to 1, C is mapped to 2. 3 is not being mapped because that is totally fine in case of functions, right? We have to map all the elements of set A. Now let's try to define domain, codomain, and range over here. Now domain is set A, right? That is A, comma B, comma C. Now codomain is set B, that is 1, comma 2, comma 3, right? Range is the elements which are being mapped, that is 1, comma 2. Now I can clearly see that range is not equals to codomain. So that is the definition of into functions. If range is not equals to codomain, that means they are into functions. And similarly, if range equals to codomain, let's say we have this case. This is set A, this is set B. Let's say we have this case, this simple case. Here range equals to codomain. If this is the case, then these are onto functions. Now, why are we defining into these categories? That will come to discussion when we are talking about bijective functions or invertible functions. So as of now, just remember this: whenever range is not equals to codomain, in that case, it's an into function, and if range equals to codomain, in that case, it's an onto function. Now, interesting conclusion out of this is range is always a subset of codomain. Now, again, if you want to bifurcate more, if range is a proper subset of codomain, in that case, it's an into function, right? If range equals to codomain, it's onto function. And if range is a proper subset of codomain, in that case, it's an into function. And in general, if we combine these two things, range is a subset of codomain, right? Got the point? Again, let's take this example. Let's say we have again modulus function, but now I'll write the domain and codomain first. So this is being defined from R to R. So this is domain, this is codomain. Now I'll get one interesting point over here. Now can I say that range is, its range equals to 0 to infinity? 0 is over here. It's always greater than 0, greater than equals to 0 actually, right? So its range is 0 to infinity, 0 pay close bracket, right? But we know that codomain is R. This is codomain. So what we get over here, range is not equals to codomain. Range is not equals to codomain. So that is why this kind of function is an onto function. Now what I can do, I can just define it from R to 0 to infinity. In that case, range equals to codomain, because I have defined codomain in this manner. In that case, this is an onto function. In the previous case, it was not an onto function, but in this case, it's an onto function. So basically, it means that everything depends on the definition of codomain. The way we have defined codomain, it will be given in the question, but the way we have defined codomain defines the type of function. If it was defined R to R, then it was an into function. If it's defined from R to 0 to infinity, in that case, it is onto function. Now, what are these tests? Horizontal and vertical line test. So horizontal line test is for 1 1 many 1, 1 1 many 1 test, and vertical line test is for if it's a function or not, checking the function. Now, how do we say that? So again, let's take examples. So again, take modulus example. Now, if I just draw one horizontal line over here, I can see that this is a line parallel to x-axis. So it's cutting at these 2 points. Both these 2 points have same value of y, but it has different value of x. So basically, two values of x having same value of y. So this is horizontal line test, which says that if it is cutting at 2 points for different values of x, in that case, it's a many-one function. If it's cutting at just 1 point, basically it's a one-one function. Very, very intuitive, right? Now talking about the vertical line test. So let's say let's take examples of y equals to x square and y square equals to x. So these are two similar kind of functions. Both of them are parabolas, but the first one is upward facing parabola. The second one is right facing parabola. Now if I draw a vertical line over here, any vertical line over here, it's going to cut just at 1 point, right? So basically for every value of y, there is just one value of x, right? For every value of y, we have just one value of x. Now, but over here, for every value of x, we have two values of y. So this is y1, this is y2. So over here, it was actually for every value of x, we have just one value of y. But over here, for every value of x, we have two values of y. This is y1 and y2. Now, remember the discussion that in our definition of function, we cannot have like this, right? This is x and this is y over here. So we are getting two values of x originating from, we are getting two values of y originating from one value of x. So this is not the definition of function, right? This is not a function. This is a normal relation, but it's not a function. So that's why a vertical end test is used to define, used to test if a relation is a function or not. Now let's talk about trigonometric functions. Are they many one or one one? So let's plot the graph of sin x. This is the graph of sin x, right? So if I draw a horizontal line over here, I can see that it's cutting at 2 points, basically multiple points. It's cutting at multiple points. So it is a many one function. But that is again true only if the function is being defined from 0 to pi or 0 to 2 pi. If we have restricted the domain from 0 to just pi by 2, in that case, it's not possible, right? It's a simple one function. But that is a rare case. If that is being defined, then only we can say that it's a one function. But in general, whenever it's not being mentioned, then trigonometric functions are many one functions. Then we can assume that they are being defined from 0 to pi by 2 or 0 to any other range, not just from 0 to pi by 2, right? So we can basically make a conclusion that all periodic functions are many one functions. How do we know that? So I'll not go into the discussion of what are periodic functions. I'll just give a brief about periodic functions, but we'll not go into technicalities in how to calculate periods, but we'll just know what are periodic functions. So as the name suggests, periodic functions are the ones which are repeating itself after a certain interval. So let's say this interval is t. So after every interval t, this entire function is repeating itself. So whenever I'm drawing a horizontal line over here, in that case as well, I get multiple points. So basically for we'll get multiple x values for just one value of y, right? So that is why it's a many one function. Now again, just like trigonometric functions, it depends on how are we defining it. If we are defining it from here to here only, from here to here only, basically in this zone only, then we are not going to get 2 points over here, right? Right. But in general, if nothing is being mentioned, periodic functions are considered as many one functions. Now let's talk about the nomenclature. Now we talked about one functions. So they are also called as injective functions. Onto functions are also called surjective functions. You just have to memorize these ones. I know it's tricky to remember these things, but you'll have to memorize it. One is called injective. Onto functions are called as surjective. And functions which are both one and onto are called as bijective functions or bijections. Now let's talk about inverse of a function. So our hypothesis is inverse of a function exists only when the function is bijective. Now let's try to prove it. So basically we are saying that if a function is 1 1 and on 2, only then we can say that inverse of a function is going to exist. So let's take again example. So this is our set A, this is our set B, this is our set yeah. Now let's say this is the inverse function. So we are defining from B to A. We talked about inverse relations in our previous lecture, right? So we just change the direction of arrow. Now let's discuss the case of many one function. Why many one function cannot be invertible? So let's say all these elements are being mapped. So A is being mapped to 1, B is being mapped to 1, and C is being mapped to 2. So we have no mapping for 3. Now let's try to invert it. For inverting it, we just have to inverse the arrows, right? So now this is happening, right? Now if we are defining a function from B to A, so first of all, we cannot have two images over here, right? We cannot have two images in the codomain for a single element in the domain, right? So for one, we cannot have two images. So that is why it's not a function. Also, one element is not being defined, is not being mapped. Now, initially it was fine over here because B was the codomain, but here B is the domain part. So for in case of functions, B is the domain and every element has to be mapped. So 3 is not being mapped, and also these are divergent rays. These are the divergent arrows actually. So one is having two images in set A. That is also not possible as per the definition of function. So that's why inverse of many one function doesn't exist. Now let's try to define a function, define an inverse of a function in case of an into function. So this is a set A, this is set B, this is set A, this is set B. So let's add one more element 4 over here. Now let's try to draw an into function. So we can clearly say that this is an into function because every element of A is being mapped to B. So that defines the basic rule of function, but 4 is left over here. So codomain is not equals to range. So 1, 2, 3 is the range, but 1, 2, 3, 4 is codomain. Now let's try to define the inverse. So for that, we'll reverse the arrows, right? Now 4 is not being mapped to any element of A. That is against the rule of functions, right? So that is why we can clearly say that an into function, for an into function, inverse is not being defined because one element or one or more element of set B is not going to be defined or not going to be mapped. Sorry. Yeah. So that is why it's not, an into function does not have an inverse function. So that is why a function has to be bijective, basically 1 1 and onto for its inverse to exist. So today's lecture was still here only, and I know that this was a lengthy lecture and there were too many concepts which were being discussed, and I'll be giving more problems in the Prep Master portal related to these chapters. This entire function chapter is going to be a little lengthy, so just be patient with it because all these concepts are the building blocks of the entire calculus. So let's meet tomorrow for the second lecture of functions, and thanks for watching.